Yes, Schur's lemma says the kernel of a yeah, that's an observation. The kernel is of a G linear map is a G invariant subspace. The image of a G linear map is a G invariant subspace. Yes.
So, but my question is, you have written that if F is a completely closed field and G is a Williams group, G is finite dimensional, irreducible dimension of a V is equal to 1. So I was totally confused with this.
No, that requires a little bit more proof. That does not immediately follow from. Okay, so what Sumit? Let's repeat his question. So what we have said is one version of Schur's lemma was that. So sure, it says that F is algebraically closed. V finite dimensional, irreducible. G is a group. Irreducible FG module or G representation. Then and G right? Okay. Now this does not follow immediately from those statements. This requires a little bit of work. Okay, so let's recall how we did this. Right? So the way we did this was proof. Let's recall the proof. This is, you have to use this. There in those statements there is no reference to any algebraic closure. This is not true. F is algebraically closed is important. It's not for nothing that we are putting it there, right? Not for just for simplicity. It's just not true otherwise. Yes, for example, in the proof we are going to use existence of eigenvalues, and therefore that is not. Exactly. Okay. In fact, using that you can construct counterexamples to this statement. If eigenvalues don't exist, then this cannot be true. Okay. You can produce irreducible representations for which this is not. For which this statement does not hold. Okay. Proof. Let phi be in NGV. Okay. Choose lambda eigenvalue of phi. Then what does it mean? Look at phi minus lambda identity. So kernel of is non-trivial. That's by choice of lambda because it's an eigenvalue, right? So that means that this has to be whole space. Now therefore kernel of phi minus lambda I is equal to V because V is irreducible. Okay, so implies phi acts by multiplication on V as multiplication by lambda. So this requires a bit of proof, namely, and it uses this. Now, while the proof is not difficult, it may not be, it's not as lying as much on the surface as the other statements we made. Those are trivial.
So sometimes I used to confuse this abstract definition like in general, in you go to the definition of representation, rho max from G to J,
Yes.
algebraically close this eigenvalue. So I have also done. But here sometimes, like you say, it's sophisticated language, people have to know.
Yeah.
Somehow,
No problem. Is this okay now? Okay. Yeah. Like I said, I don't mind repeating all this several times. Okay. I understand that these are not easy. Okay. It takes time. Okay. So you're all young. So when you have the when you are young, children are free to say whatever they want to say, right? So in that sense, you are all young. So you have the freedom to ask. You have the freedom to do what after you grow older, that freedom sort of goes away. So use it while you have it. Okay. Okay. Anything else? Okay. So what we will do today then is do a little more about. We've already proved the theorem, right? Proved our theorem on character theory. So can I erase this? So can somebody please say what the theorem is that we proved? So let us start with the hypothesis. Okay, we took base field is complex numbers because we are going to talk about inner products and algebraic closure will also be necessary. So we'll assume base field is C. Okay, and then G finite group. Okay, and the theorem says. Characters of irreducible, I'll shorten it to irreps, right? So you list the irreducible representations, rather isomorphism classes of them, to be more precise. You list them, and then character means then you are taking trace of those. So the corresponding functions on G with values in C. Right? Characters of irreps form. Yes, Suraj, continue please. Form an orthonormal basis of the Hilbert space of Hilbert space of complex valued class functions. Right, and what is the inner product? If I have F and G, this is defined to be, it is important that you take this inner product because we have said there is a certain normalization. So that it is with respect to this that it is this is our inner product. Right? So it's important, observe that these are not all functions. These are class functions. There is a particular case when you can take this to be when class functions equals all functions. If the set of class functions equals all functions, then what can you say about the group? It's abelian. So in the abelian case, you can replace class functions by all functions. Okay? And in fact, there is a theorem which says, see, so what you are doing is you are trying to understand functions on the group in terms of its representations, right? Okay. All characters are obviously class functions. So the space spanned by the characters is clearly contained in the space of class functions.
Okay, take G by G1, the commutator,
Hmm.
and so in the exercise, it's like we showed that any representation from G can be, there is a bijective correspondence between that and
Yeah, so
then we can switch to functions instead of class functions.
well, correct, you could do that, but yeah, but that's not, if you go modulo the commutator group, that's already for interesting groups, this will be maybe trivial. For example, Sn, what is the commutator subgroup? An. So it's just very small, right? While that is true, that's not what you're saying is correct, but it's not so interesting because it doesn't get you very far, that observation. Okay? Yeah, it's true, correct, but class function is? That is, yeah, that is also true, yes. Okay, what Avijit is saying is a very important observation, and in fact we use that in the construction, right? So here is, so what Avijit is pointing out is the following observation. Let chi be a function, be any function. Then if I take this in CG, right, you can form that element of CG, right? This is belongs to the center. So this is an element of CG belongs to the center if and only if we use this in the proof of the theorem, remember. This is an important observation, right? So the center of G, so center of CG has dimension equal to number of conjugacy classes of G. Equals number of This is a very important construction. Recall that when we said that, how did we prove the second part of the theorem, namely that the characters, these characters span the space of class functions. How did we do it? If you recall, we took some chi, let chi be a class function which is orthogonal to the space spanned by all the characters, to the subspace spanned by all the characters. Eventually you are going to say that there isn't such a thing except, except 0. But a priori you choose one and then you construct this, maybe with a bar here. Okay, and then you show, because it is in the center, now if you use Schur's lemma, what we did on the board, that says this operator. Now you think of it as you can think of it as an operator now on any representation. On any representation, because it is commuting with all elements of G, the fact that it is this means this operator, when you think of it as an operator, it commutes with all elements of G. Therefore, it's in end GV. It's a G endomorphism. It's a G endomorphism. Therefore, it must be a scalar. Right? That's what we used. And so we computed the trace of that. So if we wanted to show this is 0, in the recalling the proof of that, we wanted to show it was 0, and to show that was 0, what we showed that we showed that it's a scalar multiplication, and showed that the trace is 0. That's where you use characteristic 0. Okay, it's a very this will appear quite. It's a this is a sort of motif that appears again and again. Characteristic 0 will be important. Okay, to show that some scalar is, some matrix is 0, you prove that it is a scalar, and then take the trace and show it 0. Okay? Okay. Right? Okay. Now, let us do some more. I want to today start you on an example. Amit, may I have the book for a minute? So let me assign you something to read by yourself. Okay, and it is my intention today to help you get started on this. Okay, so what we have done is we have set ourselves up, right? We now the interesting thing starts. We have the basic theorem. Now we can work out interesting examples. Okay, so here is. So we will assume, so base field is C and G will be a finite group. This is our assumption for the day. Right? Okay. Now as it turns out, the representation theory of G is relevant for the structure theory of G. Meaning, to study the structure of G, you will use representation theory. So what one means by this is the following. Of course, very often mathematicians are not interested in a group because of its representations. So even more, representations are the reason why you are interested in a certain group. Okay, but for a minute, suppose you are interested only in the group, and you say, okay, I have some question about some elements in the group, or whether the group has a property. It's just a group theoretic property, right? Even then, representation theory is relevant. Many group theoretic structures are proved using representation. For example, Burnside's theorem, to give a simple example, that if the order of a group is exactly divisible by 2 primes, or 2 or fewer primes, right? If it is the number of primes dividing the order of a group is at most 2, then the group is solvable, right? That's a statement which we made without proof, right? And that is a statement, that a proof of this is something that you can read and present in a seminar. Okay, it is at that level. We could even do it in the course itself, but for lack of time we are not doing it. But it is at a level that can be done in a course within the scope of this course. Okay. Yeah, P square is abelian, but P group we have seen has non-trivial center and it is nilpotent, etc., etc. But PA-QB theorem it's called. If it has at most 2 primes dividing it, then it is solvable. It's a very, very basic, very important theorem. Now that is proved, the standard proof of it is using representation theory. Okay, original proof, I believe, is also using representation theory. Maybe there are these days proofs of that not involving representation theory, but they are, one would guess that they may be a little contrived. It's for the sake of giving a proof without using representation theory. Okay, the most natural one uses representation theory. So the point is, even if one is not interested in representations per se, but only in the group, then also representations are relevant. Okay? But anyway, it may not be incorrect to say that many more mathematicians are interested in groups because of their representations. So that's the reason why they are interested in the group in the first place. So it is important, therefore, and it's a beautiful thing to want to do, is to, given a group, list out its irreducible representation. So coming back to the 2 questions, classify the irreducible representations, and second, given a representation that occurs naturally, decompose it into irreducibles. These are very important problems. So for example, just to give you an example, how interesting it can get. Okay. So we know that Sn acts on 1, 2, 3n, right? And you can linearize this. You can make this Fe1, make this Ce1. I linearize this action and I get a linear representation, right? Okay. How does this break up as irreducible representations? Well, the answer lies in the exercises. It breaks up into one-dimensional representation generated by E1 plus En, and the other one is an n-1 dimensional representation where the coefficients of the EIs add up to 0, consisting of those elements where the coefficients of the add up to 0, right? Okay. But here is another problem. So Sn acts on 2 element subsets of I just took 2 for example. You can take k element subsets, linearize that action, and then study, then ask what are the irreducible representations in there. 2 element subsets of this. So the set of 2 element subsets of 1, 2, 3. So look at the set of 2 element subsets. I took 2, like I said, I took 2 as an example. You can take k element where k is some fixed, or you can even take Sn acting on the power set. Just take union over all k. That also you can do, right? And then ask, then linearize that action. How does that break up into irreducibles, right? You can ask that. So that is an example of this may be too trivial. You might not say, okay, this is not exciting, but already this may be interesting. Okay, how does that break up? So this is a very, it may not be incorrect to say that within that question, correctly interpreted, it encompasses a lot of mathematics. In other words, if you can answer that question in great generality, you've done, it involves a lot of mathematics. Okay, so many, in other words, many mathematical questions of interest can be framed in such a way as to be a version of this question. Okay, many things that we ask, for example, Fourier series, decomposing a function into Fourier series. Okay, that sort of within that's a standard way. This is a standard way of capturing information on Fourier series. Okay, it generalizes. It's a generalization of Fourier series. Okay, but again, for lack of time, we won't go into that. Again, it is something within the scope of a course like this, but we won't have time to go into that. Okay, so we'll. Okay, what we will do today is study the character table, so-called character table. So what you do is the following. So you want to do this. So you start with we have a recipe for this, although that might not be easy to carry out, right? What is the recipe for this? We know that V is equal to chi V, chi V1, chi 1 right, where V1, Vn is the list of irreps, and chi I means chi V of I. That is the character of the corresponding representation. So this means that inner product of this character with this character, of this class function with this class function. Okay, in the definition that I just erased. This is the recipe. So what you do is you just take chi of V, take the inner product with the corresponding irreducible representation. So and then decompose. Okay, so there is a recipe. Whether you can actually carry this recipe out is a different, maybe it's a different matter, but anyway, there is this recipe. Okay, okay. So our job then will be to write. So V1 list all the representations and find this. Okay, okay. Now, so what you do is the following. So there is the concept of a character table of a group. Yes.
This decomposition, the same that XML appeared, I give that number. That will be the same number if you decompose that vector space as an irreducible submodel.
This is a decomposition into irreducible submodel.
So that number is also the same as if you decompose the vector space and restrict your representation to that irreducible.
No, I'm afraid I don't understand your question.
I'm saying any vector space, like representation has been active on a vector space, then that vector space you can decompose it as some of irreducible subspace.
What subspace? That is the irreducible G space is just irreducible. This is it.
That is the same as
Yes.
the same number.
Yes. So this is the decomposition of V into a sum of irreducibles. Okay? Yes. Which theorem are you referring to?
underlying spaces. Probably decomposition in the linear.
Okay, yeah, no, yes, yes and no, yes. Yes, you see, the correct way to think, what generalizes both of them is the following. There is a ring. You are not looking at it as a vector space, but as a module for a ring. There, in your context, you would be looking at it as a ring, as a KT module, where K is the underlying field and T is a linear transformation of V. Okay. Here, you are looking at V as an FG module. So, the ring in question here is FG or CG for us, because the underlying field is C. Right? That is the group ring. Right? So, what you are doing is you are trying to decompose a module into a direct sum of indecomposables or irreducibles, as the case may be. Mind you, it may not be not every module. Maybe you may not be able to decompose it. There may not be a decomposition into irreducibles. It is true only if the module is semi-simple. Right? That is one of the equivalent conditions for a module to be semi-simple. Not all modules are semi-simple. Okay. However, as we have seen, for the group ring, every module is, for CG, every module is semi-simple. So, you can decompose any module, any representation into a sum of irreducibles, and this is the irreducible decomposition. Okay? Okay. So, here is what you do. So what is important is the list, or rather than maybe more than the list, the number of these representations. Okay. So you write here on this side, you write the irreducible representations, or just write a symbol for one of them. You make as many rows as there are irreducible representations. Now, there is always one irreducible representation that I know. There is always one. What is that one? Trivial one. Namely, meaning, let's be clear, B is a one-dimensional subspace and G will act on it as identity. Right? Okay. So you take this to be the trivial representation. Okay, and then there is the rest. Right? So let me write it V2, or let me write chi. So chi1, it is standard to think of well, this is true. So let me write okay, you give them names, list them, V1, V2, etc. The first one, you take it to be trivial, right? Okay. Now here, I write the character of it, but what is the character? After all, it's a function, right? So I could write the group elements here, list the group elements here, and against that group element, I write out the character of this representation, this irreducible representation, right? Okay. But this information can be compressed because we know that the character is a class function. So I need not write all elements of the group, but only one representative, only the conjugacy classes. Okay, so here I write conjugacy classes. Right? So and one is its own conjugacy class, right? So it is standard to write the identity element, and you write the number of elements in that conjugacy class. You indicate. So, and then you write C2, this is the cardinality of C2. And what do you know? It is a square matrix because the number of irreducible representations is the same as the number of conjugacy classes. So it's a square matrix, and I can write this. right? Okay. Now, so this is called the character table of the group. Okay. This is a very interesting thing about the group. You can say many things about the group by looking at its character table. And in fact, you might be amused to know that when they were classifying finite simple groups, trying to find more and more of them. Okay, now of course the theorem is proved. They would, in many cases, the character table of the group was produced even before they found the group. Okay, so some of very large dimension, you suspect there is a group of that dimension. So you produce, the theorems were proved saying that, okay, if it exists, then here it is. It must have this character table. Okay, so the character table is an extremely interesting thing about a group. Okay, so you can spend a lot of time, maybe even a lifetime, on generalizations of this. Okay. Okay, so let us start with some simple groups. So let's even start with 1, 2, 3, so on. Let's proceed so that we make sure that we understand. Let us take for the group, trivial group first. Okay, so trivial group. So how many conjugacy classes does it have? 1. So trivial group, here it is, I'll write 1 and 1. And how many irreducible representations that it have? It has just 1, trivial, and here it is 1. Correct? Okay. So now let's do Z mod 2Z. However you want to call it. Right? Okay. So how many elements does it have? Abelian group. So every element all conjugacy classes are singletons. So there are 2. Right. So this one is plus 1. So 1, 1, minus 1, 1, right? Therefore, there must be 2 irreducible representations. One is identity, okay, so this is trivial. So this goes to 1, this goes to 1, right? So here it is always 1, 1, 1. Correct? Because everything, so this is 1, 1, but what is this next row?
Square root of two square identity, so it's other than identity.
Can you think of another? You can think of this as S2. Acting on the 2 element set. But that may not be irreducible. No, 2-dimensional, it won't be irreducible. Because by Schur's lemma, we have seen that has to be 1-dimensional.
Then like G square equal to identity element in the group.
Yeah, this is the generator. This is the generator.
So we just, the B is a S and we send 1 to, we send -1 to 1.
-1 to 1 is sent here. This is the one. That if you send -1 to 1, the generator goes to 1, therefore it is a trivial representation.
So it should be the identity -1
minus 1 goes to minus 1, right? If you could send minus 1, so this is plus, okay, this is the map from plus minus 1 to C. There are two maps. One is the inclusion map. The other is sending minus 1 to 1. So minus 1, if you send minus 1 to 1, then you get the trivial representation. If you take the inclusion map of plus minus 1 into C star, so then minus 1 goes to minus 1, 1 goes to 1. Okay? This is called the sign representation. Because it is the sign of that permutation. Right? See, if you know what it means for a parity of a permutation, right? If you write it as a product of transpositions, then whether you use odd many transpositions or evenly many transpositions, it doesn't matter how you express it. That if it is odd one in one way, it is always odd. After all, you define alternating group as being the subgroup of even permutations, right? So it is minus 1 for odd permutations, 1 for even permutations. There is always that. Remember, for now, you have one more representation for Sn that you know. Namely, send all odd permutations to minus 1, send all even permutations to 1. Okay, that's another representation. Okay, so you should think of various ways of producing representations, right? It's a group homomorphism. So when it has a factor group, right, and then any representation of the factor group, you can pull back and get a representation for the. So if I have Sn, for example, Sn mod An is Z mod 2Z. So these two representations, the two representations of this irreducible representations, can be pulled back to Sn. They give you respectively the trivial representation and the sign representation. Clear? Okay. Now let's do Z mod 3Z. Right? There is only one. So 1 is done, 2 is done. Let's do 3. Okay. So this is okay. Tell me what. So let us start building now. Now, how many should I write here? 3 columns, because it's abelian. Everything is its own singleton conjugacy class. So, sorry. Okay, and therefore there are 3 things here. Of course, the first one is always send everything to 1. What is the generator there? What is the generator of this group? Omega. You know by Schur's lemma, every irreducible representation is of dimension 1. Right? Every irreducible representation is of dimension 1. So, also you can also derive it from, as Avijit was pointing it out, you can also derive it from the formula that, see, it also comes from this formula. Right? This comes from, we got this by obtaining, see, you remember this? We decompose using that recipe, we decompose the regular representation, and we found that the number of times a certain representation occurs is equal to the dimension. So you have this. Now, how many representations are there in an abelian group? It is equal to the conjugacy classes. Each element is its own conjugacy class. Therefore, there are cardinality of G conjugacy classes. Therefore, this number, this is always a positive integer, and there are at least as many as G here. So what can this be? Only 1. If it is more than 1, it will not add up to, it will become too big. Okay, that's another proof, if you wish. Okay? Okay. So we have Yeah. Anyway, but it also comes from Schur's lemma. Okay. Okay. So what is? Tell me what other representation you can have. Omega going to, of course, this is given as a sub of C star, right? See, what does a one-dimensional representation mean? It's a map into C star, right? And it's a sub of C star. So I can take the inclusion, right? That inclusion will give you 1 omega omega square, right? And then the next one is omega, you can set it to omega square. Right? And observe that this is, you know, the rows are, yes, the rows are orthonormal because that is the orthonormality of the characters. The in this case, right, because this is what is, how do you compute the, you just multiply them, and of course here if you must, for every element of the group you do it. So here, of course, since there is only one element, it is literally taking the scalar product of this with this, this with this with this, and then dividing by 3, right? Because you have cardinality of G is 3. So if I take the scalar product of this with itself, I get 1 plus 1 plus 1 divided by 3, which is 1. If I take the scalar product of this with this, I get 1 plus omega square, but I know 1 plus omega square looks like this Mercedes-Benz logo, right? Right? So that's the 3 vectors adding up to 0. So that is 0. And if I do, for example, this and this, I get 1 plus omega cubed plus so 1 plus omega cubed plus, let's see, am I doing something wrong? No. I have to take the bar. Remember, I have to take the bar. So I have to take the bar. So yeah, no wonder. If I take the bar, then it becomes omega to the 4. This becomes omega square. So this becomes omega and this becomes omega, the product becomes omega, this becomes omega square, and therefore 1 plus omega square is also 0. Okay? So, right? And now you can guess for a general cyclic group what it's going to be. What is it going to be a general cyclic group? Same. So cyclic group you can do now, right? So let us do for 4. So I will not write down the, let's just fill in the, can you help me fill in the things? Top is 1, 1. Next. So what should I write here? 1, 1, 1. Okay, well let's observe that what is the trace, 1 always goes to 1, meaning 1 always goes to the identity, and then what is the trace of that? Trace of that will give you the dimension of this representation. So the first column here is, this is dimension of V2. This is dimension of Vm. The first column is always the dimensions of the irreducible representations. Okay? So here it is always 1. Okay. Now, here what should I write? I. This is I square, which is minus 1, and this is minus I. Now, there is I here, right? So I can go to 1, I can go to I can go to minus 1. And then in I square will go to 1, and minus I will go to minus 1. And then I can also go to minus I. Very good. Minus I, minus 1, I. All right? Okay. Let us do for S3. Did I make a mistake? Just check.
Four plus four in that matrix. And this is also normal matrix.
Sorry?
You can think of 4 plus 4 matrix. It looks like the ortho normal matrix.
Yes, it is an ortho. It is an ortho. What do you call it? It's a unitary matrix. Right? It's a. Is that the correct word? U star is equal to 1. Yes. Yes, the columns will also be orthonormal, because if you know that a matrix is, if the rows are orthonormal, then the columns are orthonormal. That's an interesting fact, right? Because if A star is equal to 1, A star A equals also 1. That's, or A transpose star is also 1. Okay, let's do S3. Is this all right? For any cyclic group, you can do it now. Okay, I repeat, this is a very interesting exercise. You can, you cannot spend too much time on this. No amount of time spent on this is enough. I mean, you can just go into it as deeply as you wish. Okay, so let's do S3. So how many? This is the first non-abelian case, right? Okay. Let's understand. Non-abelian case. So there must be, because, okay, is the converse true? That is, if every irreducible representation is one dimensional, then is the group abelian? Yes? Why? Because of that. Okay. Good. Go ahead. Each one is 1.
So there should be n number of cases.
Yes. Therefore? No, go ahead, say it. Just continue your argument. It's also the number of conjugacy classes. Therefore, every element is its own conjugacy class, which means it's abelian. Right? Okay. So there must be one of one bigger dimension. Okay. Can it be dimension 3? You look at that equation. Then it will become 9. So it can only be 2. So now look at that equation. So you already know 2 of them, right? There are at least 2 irreducible representations of dimension 1. One is trivial, the other is the sign representation. There is only one 2-dimensional representation. Is that so? You can reduce this, right?
Even if we did not know that there are 2 one-dimensional representations, if we have 2 two-dimensional representations,
that already is beyond the absolutely. So there are many ways you can do this. Yes. So the numbers we know are okay. So and anyway, we also know that there are 3 of them, right? Because we know that the conjugacy classes are 3 in number. So this is 1, 1, and then I'll write one element, 1, 2 cycle here, and how many are there? 3 of them, right? 1, 2, 1, 3, and 2, 3. And 1, 3 cycle I'll write. That is this. And how many of these are there? There are 2 of them. Okay. So I have the trivial, which is 1, 1, 1. I have the sign, which tell me the numbers, please. 1, minus 1, 1. Okay. Now observe that this, directly this is not if I orthogonal. But the problem, the reason is you need to multiply. See, the inner product is over every element. So you multiply this product by this factor. There we did not need to do it because everything was 1. Okay, so there may be a bit of confusion when you see when I multiply this I get -1 but 3 times. This 1 comes 2 times. So here it is 1. So 1 plus 2 minus 3. So these two are, that's why this is it does. Sorry. Sorry.
We have trace, so we written the trace of that of a matrix acting on some element of the conjugacy class.
Yes.
So for that element we take the trace of that matrix and we write it.
Yes.
And to say it is orthonormal, we just have
No. This recall what our inner product is. It is the summation over every element of G, not over conjugacy classes. Okay. So this you would want to do it 3 times. This -1 for 1 2, -1 for 1 3, -1 for 2 3. So this will occur 3 times. So this becomes -3. This will occur twice. This will occur once. So 1 plus 2 minus 3. So that is 0. Okay. Okay. So and the dimension of the so this is called the standard representation. Okay. What is the standard representation? It is the one that Surajit mentioned. That is, you take the one. So the standard representation is Sn acts on 1 2 3 n. So this is the defining action, and then you linearize this, and you have an action of Sn on our underlying field is C, so I'll write C, right? And then the subspace standard representation, let's identify it as a subspace. This is lambda 1, so E1 this is sub of that. This is the definition. So by the exercise, this is always a irreducible representation. That's the claim. Okay, it's an irreducible representation. Okay, so in that case, let's compute what its dimension is. So here you will write the dimension, right? So I'll write 2. So what should I write here? So what should you do? You should take a basis for this. I mean, okay, let's do it. There are many ways of doing it. You can do it, you can be very clever with these computations, but for a beginning, let us just think through what you want to do. Take a basis for this, right? And then write out the matrices for those 2 elements on that basis. Okay? You could do that. That's one way of doing it. But here is another way of doing it. Okay? So you know that, so I want to, this is what you want to do, right? You know that the defining, how does this break up? This representation must break up as a sum of irreducible representations. What are the 2 irreducible representations? One is the standard, and the other is on the E1 plus E2 plus En, on which it acts how does Sn act on that? Trivially. You take E1 plus E2 plus En, what does, you just permute those elements. So it fixes that vector, right? So it's a trivial representation. Right? So now I take chi of defining equals chi of standard plus chi of triv. Right? What is this? This is the representation where this is very easy to do. This is just a permutation. This is just this. You write it as a permutation matrix. Right? So where does 1, 2 go? So let's write here chi of definition or defining. Let's write chi of defining underneath here. So where does 1 go? To what matrix does it go? 1, 1, 1. Identity matrix. So here it is. Of course, this is always the dimension. Right? Where does 1, 2 go? It flips 1 and 2 and fixes 3. So it goes to 0, 1, 0, 1, 0, 0, 0, 0, 1. 1. And where does 1, 2, 3 go? It does not fix anything. So it goes to 0. Now tell me what chi standard is. You subtract this from this. 3 minus 1, 2. 1 minus 1, 0. 0 minus 1. Right? So you can be very clever with the computations. Yes, that's a good point. Let me make a comment. I'll make that comment. It's one of the things I wanted to do. So today, I'll do that. Is this right? So it will be very interesting to do various examples. For example, dihedral groups. Right? How do you write out the irreducible representations? Okay? Okay. Now, let us do, Avijit is talking about orthonormality in this case of the, we know, so of course we know that these as functions with our inner product, if I think of the rows as functions on G, and with the inner product we have given, then they are orthonormal, right? But suppose I want to think of I don't want to think of them as functions, but rather this as a matrix and think of its orthonormality. It's obviously not orthonormal, right? Because this is 1, this is minus 1, this is 1. So this is the inner product of this with this gives you 1 rather than 0, right? But there is a small thing you can do which you can do to change this, which will, so observe the following. So, if we multiply each column of the character table by, this is the cardinality of the conjugacy class corresponding to that column. Maybe there is a square root also. Let's put it. That's a highly alliterative sentence, right? Cardinality of the conjugacy class corresponding to that column. There's a lot of C's there. Okay. Right, suppose we do that. I take this column, I multiply by, in this case I would multiply by, so 2 by 6 square root of, right, that is 1 over square root of 3. I modify this by 1 over square root of 3. I modify this by 1 over square root of 6. I modify this by 1 over square root of, sorry, I made a mistake, didn't I? This is modify this by 1 over square root of 2. This I modify by 1 over square root of 3. And this I modify by 1 over square root of 6. Then I claim that the rows are orthonormal. Then the rows are orthonormal. This is just, why? Exactly. So what I know is, if I multiply this by, this is just, right? Because I multiply this, and here is a square root, here is a square root. So the square roots will just give me C over G. So, but that C is just precisely, right? Correct? So, then the columns are orthonormal. Right? So what do we get out of this? It's the following. If I take, so you get the following observation from this. So see, we have been taking inner product where you take the inner product with let us look at the columns, right? Let us look at the columns, and then I will get sigma. You will get the following over irreducible representations. Chi of C1, sorry. Yes, that's correct. So I take the column now, right? If I take this column, I multiply this column, its conjugate by this column, right? So okay, and then if I have to multiply by this, right? So what so I get C1, C2 by G is equal to delta C1, C2. Right? So let me write it here separately. So what you get is the following. If I take summation over irreps of chi, so this stands for as element of a conjugacy class. So I'm abusing notation. I'm writing the conjugacy class itself there. Okay? So this is equal to, if I unwind this, so if I take it to the other side, it is either 0 or 1. If it is same conjugacy class, it's Ci Cj, let's write. If it is the same, then what do you get? If you take it to the other side, I'll get G by C. Okay, so what have we done? What is the proof? We took our orthonormal. We know that we know that the characters are orthonormal as functions for our inner product. So using that, we normalize the columns, renormalize the columns by multiplying by that of the character table, and concluded that the rows of the resulting normalized character table are orthonormal. But then the columns of such a of the normalized table are also orthonormal, and you can express it like this. Okay? So the character table has many interesting properties. It's, you know, I couldn't, I mean, I know maybe one or two, but it has enormously many interesting properties. Yes, everything has applications. Everything has applications. Yeah, so which tables can occur as character tables? So these are all interesting questions, yes. Yes. Yes, you can say that it is the character table of S3, surely. Right, so well, okay, there are interesting questions you can ask. Okay. So let's see. So I want to, in the final 5 minutes or so, let me do one more thing that is done in the notes. That so all this is in the notes. Those 2 pages of notes, or 3 pages of notes. The 3rd page is mostly one example. Okay, so we are on the 2nd page of those notes. Okay, the character, we don't talk of the character table there, but this is done in the notes. I hope I have done it correctly. Just check, I've got this correctly, right? Yes, I've done it correctly. Okay. Let us just verify this in this case. I'm just so let's take this column and this column. So I multiply. So if I multiply, normalize by, let's just do, right? So if I multiply this with this, I get 1 minus 1, 0. So that's indeed 0, right? So if I do it with itself, I get 1 plus 1, 1, which is 3, right? So I should be getting 6 by 2, which is 3. It's all right. Okay. Okay. So let's do one more important thing. So question is, how much, so you have decomposed your representation into irreducibles, right? Now there's a question of uniqueness. How unique is this? Now let us take, I mean, just to give you a trivial example, if I take the trivial group, any vector space is a representation. What is an irreducible representation? It's a one-dimensional subspace. And we know that a two-dimensional subspace can be broken into 2 lines, sum of 2 lines in any number of ways, right? Right? We are over a complex number, so it's an infinite field, so it can be broken up in any number of ways, right? So there is, so obviously if you are going to say, okay, here is my copy of that irreducible representation, you can't talk of a single copy being unique. There is no uniqueness. However, okay, so here is a statement I want to make. If V, so this is called typical components. Right? If V is equal to, so again assumptions are there. See, G is finite and we are over C. Base field is C, right? Let's just assume this, we are working over. If V is equal to V1 this is bad notation, I'll write the same thing again. No, this is, see, I hope, you know, this is bad notation, right, okay, let's see. Yes, I want to speak of two different decompositions, but we know that the numbers are the same, right? So, okay, so let's write it like this. Okay, let's write right. Two irreducible decompositions, B two decompositions into irreducibles, into meaning as direct sum of irreducibles, right? We cannot say anything about, even after permuting, you cannot say anything about V1 and W1, V2 or W2. There is no, see, the number of pieces here is the same, because it is you can say that now if you list your irreducible, okay, let's use a different notation here. Let me say U1, U2, etc. Because let me keep V1, V2, so let V1, Vn be the irreps of G over C. Let's keep that notation. So I look at how many U's are isomorphic to V1 here, how many W's are isomorphic to V1, that number is the same. Look at how many U's are there which is isomorphic to V2, how many W's are isomorphic to V2, that number is the same, right? Because it's the number of copies of V2 that occur in that decomposition. That number is just chi V, the inner product of chi V with chi V2, chi 2, right? That we have seen is the same, right? But you cannot say anything about U1 being, after permutation, U1 being isomorphic to equal to W1. You cannot say anything like that. However, the following is true, and that is, it will have to be isomorphic, but we want equality. See, I say like, the two-dimensional subspace, you can write like this two lines or these two. Any two one-dimensional vector spaces are isomorphic, no problem. It's not isomorphism. We want equality as subspaces. That's what we are looking for. However, it's okay. If you write, collect together all the ui's that are isomorphic to V1 right. So, and write V is equal to U, let me write for it, let U1 be their sum. It's a particular, so you take your decomposition, collect together all the ones that are isomorphic to V1, collect together all I can write this. I collect all together, those are isomorphic to V1, collect all those are isomorphic to V2, collect all that are isomorphic to Vn. Similarly, write of course some of these could be 0. If for example Vn does not occur, this is 0. Okay? Then here is the thing. Then they are equal. I'm not writing isomorphic. It's obvious that they're isomorphic. They are equal as subspaces. So while you may have done something and I may have done something, and there is no guarantee that the subspace you choose and the subspace I choose, if you fix one irreducible representation, let's say V1, collect all your copies that are isomorphic to V1, I collect all my copies that are isomorphic to V1, and look at the subspace, the total subspace we have. That subspace must be the same. This is called the isotypical component. Okay? So this equality, so we need to prove this. I will do it. It's an interesting proof. So again, something that you might not have, it's very simple idea, but it's good to think, if you think abstractly, it is very simple. Okay? But we will do that next time. All right? Okay. So this is called the isotypical component. Okay, this is called the isotypical component of V corresponding to Vj. See, what does iso mean? Isobar means it's a line which connecting all the things with the same pressure. Isotherm means what? The line connecting all the places with the same temperature. Isotypical means you collecting together all the things with the same, which are isomorphic to that type. So the isotypical component is unique. Okay, it's a subspace. It's not irreducible. If you break up that isotypical component, you will see several subspaces, but several irreducible, but all of them will be of the same type. All right? Okay. Like I said, it's quite simple to see, and with this, we'll be done with this proof. I will call an end to group representation theory. We will move on to, we will come back, we'll do in the following sense. I want you to do the problems in 19.1. So anything more I do on representation theory will be restricted to discussing problems. Okay? So now I have done my job, you have to do yours. 19.1 you have to do. Okay? We can discuss. Okay, so one thing. Second, we'll do quickly semi-simple rings. The part on semi-simple rings, I don't want to spend too much time. I want to spend a little time, maybe I'll just state the main theorems and point out how group representation theory is an application of that. Okay, I'll do that.